Hello, everyone. Group Five's topic is all about the try data structure. I'm Tanyakal, and I will be presenting the first part of our presentation. So, what is a try? A trie is also called digital tree, radix tree, or it's more commonly known as the prefix tree because its niche is all about prefixes. An ordered tree data structure that is used to store a dynamic set or associative array where the keys are usually strings. Unlike the previously discussed trees, keys for the try are strings. So it can be like characters, strings of numbers. It is useful for storing strings of digits or characters. So it's just not characters, it can also have digits. So a trie is a tree data structure that allows strings with similar character prefixes to use the same prefix data and store only the tails as separate data. So as shown here. What's this word? So this word here, Dobby and Draco, it it's different words, right? But it has the same prefix, which is D. So it shares the same node here, D. And then it ends in different tails. Here, ang tail ani is Obby, and ang tail ani is Draco. So it's Dobby and Draco, it's separate. Different tails, separate data. A tree is one character of the string is stored at each level of the tree, with the first character of the string stored at the root. So here, one character is a different. I one character is one level. So the more characters your string has, the more levels your tree has. So, quick background. In 1912, Axel Thue described tries in theory for sets of strings. And then a few years later, few decades, Rene de la Brionde introduced tries for computer applications. And a year after that, in 1960, Edward Fredkin independently described the structure. And he was the one who coined the term try from retrieval. So try is actually from the word retrieval. So, diba, retrieval. So, you might be wondering, ano, try. Why is it pronounced try instead of tree? Because it's retrieval. Because tree sounds the same as the tree. And tree is like the more common term. It's like a type of tree anyway. So, it's gonna be called tree if ever. So, that's why it's called try instead. Para try tree. Yeah. So, that's the fun fact. The name emphasizes fast retrieval. Properties of a tri-tree. Alphabet size. Each node can have up to 26 children for English alphabets or more depending on the character set. So, for each node, diba, there's like a parent node and then children. If ang English alphabet ang imong character set, which is A to Z, 26 characters, a node can have up to 26. And all those nodes, 26, can also have up to 26 children. But it depends on the character set. You can also add other sets like digits, but yeah, character English alphabet characters are more common. So the root node is typically empty, unlike other trees where the highest number or the lowest depends is usually on the root. End of word flag, a Boolean value indicating if the node marks the end of a valid word. So basically to determine if a a string is a complete word, there has to be like a Boolean value indicating if the node marks the end, if the node is a complete word na. So common operations searching, basically type in a word and then it returns if it is a valid word or not. And insert, which is you can insert a word, you can add a word to the tree. Deleting, you will remove a word, you can remove a set of a string from the tree, basically. But it won't delete the node if it's shared with another string that's not yet deleted. And prefix searching, the difference between searching and prefix searching is that for searching, you have to like search, when you search like a whole word, like let's say uh dog, you search the word dog, it also returns the exact word like dog. Whereas a prefix searching, you can just search like do, and then it's gonna return back like words that start with do that exist. So that also includes dog and maybe other words like if na doll or like mm, do, what's other words? Do dot. Yeah. So these common operations will be expounded more later at the structures by Annalie. So the time complexity for tri-trees, actually the it scales with key length, not data size. So unlike other trees na it scales with the data size, which is ON, it actually scales with the key length, which is like string length, the level length, insertion, deletion, searching. It scales with M is the key length. So yeah, a structure of a trie. So as you can see, there's a root node here, it's empty, and then it branches down to a an element, a value, a character. So let's start here. So it's T. Let's see the words here. It's try. T. What's next? Ang next letter is R. So it's here, R, and then Y, Y. So there's gonna be a Boolean value indicator that um sa says that it's a complete word. It's not shown here, but it's supposed to be in the code. And the next is try, T, R, and then it's not Y. Let's try. So it goes here, I, and then E. And another Boolean indicator that indicates na word niyang try. So another word here, still B. So T is not R, like the last two strings. So it branches into its own here. O, B, Y. Na Boolean indicator, na word siya. So that's gonna be it for the T section. And then another section, CP. So C, it's not T, so it's gonna be another one from the root because it's the first letter from the root C, and then P, and E. And a Boolean indicator na complete word niya ang CPE after the E. Next is bat, BAT. So B, first letter B, straight from the root, B, and then next A, and then next is T. So, but it's a complete word, right? So, after the T, there's gonna be like a Boolean indicator na ang T, BT, bat is a complete word. But we can still continue after. We can still have another character na connected sa T, which is HE. There's another word, B. So, there's like an indicator naman, diba? Here, bat, that's a word na. And we're still gonna continue. So, after the T, there's H, and then E. So that's another word, bait. So after the E, there's gonna be a Boolean indicator. Nah, it's another word. Yes, bait is a word. So yeah, then a bait. And two beats here. So that's the basic structure of a tri-tree.
So hi guys, here's a visual of a chai. Each path from the root to a marked node forms a word. In this example, we've inserted multiple words into the chai. Chai, chai, bath, bath, Toby, and CPE. All of these words share characters with others, but the chai manages them in a compact and efficient way. Chai support four main operations, by the way: search, which is to check if a word exists, insertion, which is to add new words, deletion, to remove words safely, and lastly, prefix matching or searching, to find all words that start with a given prefix. Let's take a closer look at how searching works in a chai, using just one example, the word Toby. We'll go step by step through the chai, explaining what's happening at each level and what the structure is, checking along the way. To begin, we want to know, does the word Toby exist in the chai? We'll process it one character at a time. T, O, B, Y. We start at the root node of the chai. This root doesn't contain any letter, it simply acts as the starting point for all words. The first letter of the word we're searching for is T. We look at the children of the root and check if a T node is present. In this case, there is a T node connected to the root. So, we move down to that node. Now we're at the T node. The next letter in the word is O. We look at these children and ask, is there an O node directly under T? Yes, there is. We move to the O node next. At this point, we've matched T and O. The third character in the word is B. We now check the children of the O node. Is there a node labeled B? There is. So we continue the path by moving to the B node. Now, we've followed the letters T, O, and B. We're now on the final character Y. We examine the children of the B node and check whether a Y node exists. It does. So, we follow the edge and move to the Y. At this point, we've successfully followed the full path T, O, B, and Y. But the search isn't complete just yet. Even though all the letters exist, we need to make one final check. We ask, is the Y node marked as the end of a word? In a chai, we only count a word as valid if its final node is marked to indicate that a word stops there. If it's not marked, the path might just be a part of a longer word, and we can say that the full word exists. In this case, the Y node is marked as the end of a word. So, we can conclude that Toby is stored in the chai. Now that we've seen how search works in a chai, let's walk through the process of inserting a word step by step. In this example, we'll insert the word top. We'll explain not just what happens, but why each step matters and what the chai is doing internally as the word is added. We begin at the root node, the base of the chai. From here, all words branch outward letter by letter. Our word is T, O, P, or top. The first letter is T. We check if there is a child node labeled T under the root. Looking at the structure, yes, T already exists. That means we don't need to create a new node for T. We simply move down to the T node. Now, the second letter is O. We check the children of the T node. Does an O node exist? Again, yes. We can see it in the diagram or structure. The O node is already part of other words, like to and Toby. We reuse it. Now we're at the O node, having followed T, O. What about P? We now check for the third letter P. Let's look at the children of the O node. According to the diagram, O already connects to B as in Toby, but we do not see a P among the children of O. This means P is missing, and this is the moment where insertion actually modifies the chai. So now we create a new node labeled P. Connect it as a child of O. This is the only new node added during this insertion. After adding the P node, we need to do one more thing. We mark this P node as the end of a valid word. That's how the chai knows that top isn't just a path, but a full word we can search for later. Without this marker, top would just be a partial path and searches would recognize it as a word. What changed in the chai? Let's recap. T already existed, we reused it. O already existed, reused again. P was missing, so we created it. Then, we marked P as a valid word ending. That's it. The structure is updated, but only where needed. This is how tries stay efficient. Common prefixes are shared, and only the unique suffix is added. In this case, just one letter, P, was added to support a brand new word. If top is inserted again, let's say we insert top a second time, the try will follow the same path, TOP. But this time, since all letters already exist and the P node is already marked as a word ending, no changes are made. The structure remains the same. The insertion ends early. This shows how tries avoid redundancy. Let's summarize what happened. We started with a try that already contained words like to and Toby. We inserted top, T and O were already there, so we reused them. P was missing, so we added it under O. Then we marked the P node as valid word ending. Just one new node, one new marker, and the word was added. That's the full insertion process, directly tied to the structure you're seeing. Now that we've covered searching and inserting, let's go over the process of deletion in a try. This one's a bit more complex because we don't just remove letters blindly. We have to make sure that deleting one word doesn't accidentally break other words that share the same path. In this example, we'll delete the word shy from the try structure we've been using. Let's walk through the process together. Start from the root, we begin at the root node and look at the word letter by letter, TRY. We ask, does the word try exist in the try? Just like in search, we trace the path. First, we go from root to T, which exists. From T, we look for R, yes, it's there. From R, we look for Y, also there. So far, all three letters are present, and then we reach the Y node. We check, is Y marked as the end of a valid word? Yes, it is. So we know the word try exists. That means deletion is possible. So the next step is unmarking the end of word flag. The first step in deletion isn't to remove nodes, it's to unmark the end of the word at the last letter. So we remove the end of word flag from the Y node. This alone is enough if other words share the same path. We stop here and keep the structure. But let's keep going and ask, are any other words using the Y node? The answer is no. There are no words like trying or tries continuing from Y. No children below Y. So now we can remove the Y node completely. It's no longer needed. Check if R has other children. Now that Y is gone, we look at its parent, the R node. We ask, does R have any other child nodes? This time, the answer is no. Looking at the try structure, R is also used by other words. If we remove R, we'd break those words. So we stop here. R stays. Only the Y node is removed, and the rest of the structure remains untouched.
For the advantages and disadvantages, the try its advantage is that it has fast search, so it depends on the length because when you traverse, it goes down the path of the string, right? So the length of the string. It supports also alphabetical order. Like this allows ko an alphabetical traversal. That's why it's useful for autocomplete or dictionary style applications. It's efficient for prefix matching. So that's why it's called prefix tree. Because it katong kuan prefix searching niya na feature. And there's no hash function needed. So there's no like collisions or no need to resize. Disadvantages. So high memory usage. Because each node Each try node it, it contains pointers for every possible character. So like for alphabetical, it contains like 26 pointers for lowercase letters. Yeah. So each node na, even if null ang kuan, even if null ang pointer, it's slower than hash table lookups for very short keys. So hash table can retrieve a key in 0 1 average time, regardless of key length. Because on tree it must follow a path of nodes, one for each character. So like so length should so when it comes to short keys like say mga 1 to 3 characters, mas slow siya kaysa sa hash. Needs optimization for large datasets. If like with millions of entries, a basic guy can consume a huge amount of memory because like daghang kay data, daghang kay mga deep branches na gamit ang words. That's why it can make traversal slower. Like some kanang connected sa here, this bullet here, inefficient when a key is too long. So if keys are very long, let's say mga link, mga URL, it adds more levels because it traverses down a string, right? So it's gonna it's gonna have really many levels. This which leads to increase the lookup time and memory usage. So in some cases, hashing is better. Some games, word games mostly like Scrabble or Wordscapes, basically like if mag-input kag word and if it's an actual word, the try determines if it's an actual word. That's why masakto yung kuhan. So Wordscapes when you connect, and if it's a valid word, ma-input. Search engines like autocomplete, like sa Google when you type something sa Google, notice how there's like suggestions with complete words na. It's also the try to predicting what you're going to type by prefix matching what you've already input, matching it with other valid stuff na. This also is also similar to how dictionaries work like on your phone. Firewalls, IP address matching. So like when your router kanang receives data packets, it like it reads the where the data packets receiver is, like who the receiver is. I mean, what IP address the receiver is. So, like numbers, but not digits. It also works with digits. So, like 1.192 something. Not there's like similar IP addresses, right? It reads the correct one. It matches the string, the, and then it sends it to the correct IP address. So, try versus other structures. So, search time really depends on the length sa imong gikuan. Compared to the others, yeah, hash tables O1, BST, log and linked list O1. So I guess ang linked list ang pinakakuan task of search time. Try memory, yeah, it takes a lot of memory ang try compared to the others. But order preservation, yes, same as BST, while others no. And here is its niche, like, where it exhausts prefix matching. Is why it's also called the prefix tree. It's excellent at this, and the others, not so much.
Good morning, everyone. I'm Kane Benitez, and now I'm going to explain to you the Trinode structure code. So, first, we have here our struct, our Trinode. Now, here we have our uh, pointer, Trinode, pointer to children. Children alphabet size is an array for the possible child nodes, mainly 26 or 4 lowercase letters. And here, Boolean is end of word. This ensures that we can differentiate between the prefixes. For example, car and full words cat, car cat. It's like a flag. Okay, now here we're gonna create a node below. First, we're gonna dynamically allocate memory here, malloc. Now we need to initialize all children to null. That means no letter have not been added yet. Okay. Now we're gonna move on to the insertion part of our code here. Okay, when inserting in a try data structure, we're gonna use the function void insert, and it doesn't return anything. Now here we have the try node pointer to the root. This pointer to the root node of the try. So here, this is where our word insertion starts. And this const char pointer key is the word we want to add and should passed as a constant character array string. Now we're gonna initialize the pointer for traversal. So here it's try pointer node equals root. We store a reference to root in node so we can traverse to the try without modifying root itself. Now we have to. The next step is we have to loop through each character in the word. So here it's our code for int I equals 0. So this loop moves character by character. So in the word key, we're gonna process it until it reaches the end 0. So 0 is null, is a null terminator string, and key array I gives the current letter. Now after that, we have to convert character to try index. So here index equals key. As you can see here, this converts the letter into a numeric index. So it's from 0 to 25 since the alphabetical size is 26. And also by subtracting the here A from the current character. So to have that as example is string of A minus string of A equals 0. It's index for A. And string of B minus string of A equals 1. That's index for B. And string of Z minus string of A equals 25. That's index for Z, since that's the last number of the alphabet. Now, after that, we're going to check if the node exists for the letter. So here, if not node pointer children, array of index. If no node exists at this index, then we need to create a new try node. Now, if we need to create a new try node, here's the code. Node pointer children. Wait, yeah, here. So we're gonna call create node. It's a helper function that allocates memory for your new try node. So yeah, we're basically done in our insertion here. I wait. No, no, no. We need to, after creating a new node, we need to move to the next node, which is here. Node equals node here, not here. Now we're gonna shift focus to the newly created or the existing child node. This is actually the crucial part in the code since we need to follow the path in a try and should keep inserting letters. So after that, we're gonna close the loop. So that means that all the letters have been processed. And now we need to use this flag. So is end of word. So actually, what this do is it flags this node as the end of a complete word, and it ensures that words uh, can be distinguished from their prefixes or try. Hmm. So okay, let's now move on to deletion. So here's the code for deletion, guys. So of course, let's define first. We're here to delete or remove a word from the try. So okay, so this code consists of a recursive helper function, this delete helper. So inside this delete helper is the try node pointer root. This is actually the current node being checked, and the const char pointer key to the key is the word to delete. So here, this is the word to delete. It is passed as a string, and int that tracks the letter position in the word. So we need to find our base case first because this is a recursive function. So here, this is our base case. If not root, return false. So this means that if the node doesn't exist, we return false. Or basically, if the word is not in try. Now we have to process each character, or we call this a recursive call. So this is code here. If he what this does is this checks if we've reached the end of the word. So if not, we're gonna continue processing to the next letter. Now after that, we have to convert character to try index here. Index. So this maps letter A to Z to an index 0 to 25, basically the number of letters in an alphabet. After that, we're gonna uh, recursive call to the next character. So here, if statement here in my cursor. So what this does is it moves deeper into the try by calling the function delete helper on the next letter. And here it increments the depth. It ensures that we progress on each character or character by character. Now, I think this is optional. No, it's yeah. We have to do this into free memory. So here, free root, because if the child node is no longer needed, we deallocate memory and we have to set it to null. Yeah. Now, return. This means that we have to check if this certain node can be deleted, right? So the function only deletes nodes that are not part of the other words. So if root pointer is end of word is equal to false, then the node can be deleted. And here also we're doing the same thing. We're doing the flag thing, the is end of word. So that means that we've reached to the last letter of the word. Okay. After that, we're here. We are gonna we have the wrapper function, the void try delete try node. This basically calls delete helper and starts deletion from depth equals 0. And the purpose of this function is it keeps the code clean and easy to use. So that's all for deletion. Now we're gonna move on to wait, where is it? We're gonna move on to searching. This is the code for searching. And first thing we do is we need to declare a function. So this is our function, our first function, bool search. This bool search function defines or returns true or false depending on whether the word exists. And try node pointer root, it is pointer to the root of the try. The root of the try is the first. Uh, yeah, you know that already. And here construct. This is the word that we want to search for. Okay, it's the same as what I've said in deletion and insertion. Now we're gonna initialize pointer for traversal. Okay, try node. It's the same things, the same process in every property. So it stores the reference root node. So it allows traversal without modifying the root directly. And now the next step is we loop through each character here. It iterates to each character in the word and stops when it reaches zero. Uh, dash zero. Uh, dash zero is like an indicator or it marks the end of the string. Now, same thing again, we need to convert the character to try index. So it index here. Basically, what this does, again, is it maps letter A, string letter A to string letter Z to the index values 0 to 25. I mean, it's for faster arrays access. After that, we have to check if the node exists. If the node for this letter doesn't exist, then here it returns false, meaning word is not found, and this stops the search early. After that, we have to move to the next node, which is here, node equals node. It advances deeper into the try character by character. So if all characters exist, we reach the final node. Now we have to check the flag again, the end of word condition here. So this returns true only if the final node is marked as the word's endpoint. So what this does is it prevents false positives, prefixes like car that it doesn't match to cart. The next process here, property is prefix searching. It's different from search. It's not that different from searching, but here we're gonna search using prefixes, and the output should display all of the words that corresponds to the prefix. Okay. First, here we're using what's this? Okay, this is a recursive function again. A recursive function that gathers words, store and try. So I don't have to define each of the elements here since I've already explained it in the other properties. So need to check if we've reached a complete word. It's the first step. If this node marks the end of a word, we're gonna print it. Now here, the buffer thing. What this does is um, it adds a null character to mark the end of the string. It's the same as before, and it prints the word stored in the buffer. Okay. So after that, we're gonna use the loop. Need to iterate over each child node, right? So it loops through like 26 possible children. Now, after that, we have to move deeper into the try and build words. So here, the if statement below. So if a child exists, it adds a letter. Need to add its letter to the buffer. Here, a plus I. And we need to call the function collect words recursively, moving deeper into the try. Now, after that, the next step is to display words that matches a prefix. So we have a function here below, display words with prefix, the same contents. So what this does is it searches for words that match a given prefix. So here, the try node pointer, this is the starting node or basically the root, and the const char is the prefix to search for. Okay. So the first condition is if, so okay, here, if statement. So if the prefix doesn't exist, we're printing a message here, printf, no words found with prefix. So if a letter in the prefix is missing, the function stops and prints an error. Now, we call the function again, collect words, to uh, find or gather the matching words here. Wait, yeah, buffer. So what this does is copies the prefix into the buffer to maintain the existing letters, and it calls uh, collect words function, uh, which collects and prints words that match in the prefix. So that's basically it for the prefix searching. And I'm also gonna show you the code. I'm gonna run the code to see if what I've explained makes sense and to ensure that this try data structure is working. Wait, hold it, pause. Wait, I'm gonna open first.